Hello everyone, welcome to Recitation 5 on Mechanics and Materials 1. Today we also have 4 questions to go through together. So this is the first question. We have a plier as shown in the picture, and we apply 2 forces of, let's say, 20 Newton at the end of this plier, at the handles, and usually you do it, or let's say you keep these pliers in one hand, right? So these are the 2 forces you apply. These are your external forces, and they obviously are in equilibrium, right? So they cancel each other. So that's what you apply to the system. Now, as a result to your applied force, what happens is that you would get internal forces and moments in that plier, right? So you can imagine, if you push this thing too much, you're going to break it. So there is something happening inside it. And this question tries to analyze that. So basically what we want to do is to find internal forces and moments at this cross-section, so at C, and also internal forces and moments at point D, but with a, let's say, with an angle 30 on that cross-section. The dimensions are given here. At point A, you have a pin. So basically what happens here, or the way you should look at it, is that you have 2 pieces. So this is piece 1, okay? And then you have this other piece, piece 2, which is behind this. And you can imagine it's basically a symmetric problem, so we can analyze each of the 2 pieces, right? But what happens is that, let's say, if you analyze the piece on top, so if you look at this one, you would have a force from pin at A to the top part, or to the part in front of us, which the opposite of that would be applied to the part behind. So there is a force, which is completely internal, by the way, but when you look at the, let's say, the part closer to us, we would see it as an external force. So let's call that, I don't know, FA. Okay? So this is a force from the pin to the part in front of us, or closer to us. Then obviously the 2 ends of the plier themselves, they also apply a force to each other. So let's call that FB. And then again, everything I am doing is basically on this outer part. The opposite of that is on that part behind, okay? So we are going to analyze this. Now, what you want to do is first to calculate the internal forces and moments at point C. In order to do that, we are going to just basically cut the structure here. And then when you cut it there, either you cut it from right or left. Obviously from right, it's simpler, it's shorter. So we are going to cut it from right, and then we write the equilibrium for this red piece that I just drew here. Okay, so that piece, if I can replicate it, it's going to look like this, for instance. Now, at this point, you have a force FB, and here, at the end, you have NC, that's the normal force. Then you have the shear force, and you have a moment at C that is counterclockwise. Okay, please pay attention that we draw these forces and moments in, let's say, in accordance with the convention that we defined previously. So if you remember, we said if you have a little piece, the plus directions for shear forces are like that, for normal forces are like that, and then for moments are basically like this. All right? So now you have this little picture. We have 3 unknowns plus FB. So what we need to do is to calculate FB first, and then we would have just 3 equations, 3 unknowns left for that. So pay attention that FA and FB are just 2 unknowns for the whole structure. So by just writing equilibrium, you can calculate this. In the question, you don't really need FA. So we don't have to calculate it necessarily. But for FB, all you have to do, for instance, is to write the equilibrium of moment with respect to point A. If you do that, then you get no moment from this. Then you only get a moment from FB that is multiplied by the distance here, 40 millimeters. And that must be equal to the moment that you get by the force 20 that is multiplied by the distance here, 120. Okay? So basically 120 times 20 must be equal 40 times FB. And from that, you can get FB equals 60 Newton. Okay? And that is, let's say, an upward force. That's the way that we drew it. Now, you come back to this picture. You know now this thing is 60. You have three equations, three unknowns left, and we just get those from the equations. So let's write those equations. The first equation is sum of the forces, let's say in y direction is 0. That immediately tells you that VC is equal minus 60, right? Because FP is 60 upwards. Then you have sum of the forces in x direction is 0. Well, there is no other force than NC in x direction, so that is 0. And then you would write equilibrium of moments with respect to point C. Again, here I mean with respect to point C. And assuming that counterclockwise is positive, what moments do you have there? You have here moment C itself, which is a clockwise. So that comes with a minus. And then you have FB, that times distance from point C. The distance from point C is 15 millimeters. So it's FB times 15 is 0. And therefore you get MC equals 0.9 Newton meter, or 900 Newton millimeters. All right? The important thing, again, is to pay attention. Here, I mean moment at point C. Okay, so here when I say MC, I am talking about the MC that we showed here. This is the moment at point C. In the equation, I mean the sum of the moment with respect to C. We discussed this. You can use different notations if you get confused, but I don't think it is confusing. It's usually clear from the context. All right, so that's that. Now we have the reactions at point C. Do you have any question? What we want to do next is to basically repeat exactly the same process here. Now, again, for that, you can cut it from the right end, or you can cut it from the left end. I'm going to cut it from the left end just for the fun of it. So if you cut that from left, you get something which looks like that. So you get 20 here. Then again, we will draw the forces as we do. So at point D, that would be towards out. So that's our convention. Then this would be our convention for VD. And then moment would be like that. There is only an angle here given in the example that is 30 degrees, which also means, you know, this angle here is also 30 degrees. Okay, so if you think this is, again, your XY coordinate system, as we usually do, we want to write our equilibrium equations now for that piece, which is, again, easy, right? You have three unknowns, three equations, you can calculate it. So the first equation would be sum of the forces in X direction is 0. Sum of the forces in Y direction is 0. Sum of forces in well, with some of the moments with respect to, let's say, point D is 0. And then again, assuming that we use our usual convention for directions, in x direction, what do we have now? We have ND cosine 30 degrees plus VD sine 30 degrees. That is 0. These are the only forces in x direction. In y direction, you would have ND sine 30 degrees minus VD cosine 30 degrees plus 20 is 0. And with respect to point D, you would just say, again, MD, that is now in counterclockwise direction, so that is plus. And then the distance here between point D and point, well, the point that we apply the force 20, the distance is 80 millimeters. So you get MD minus 80 times 20. 20 is the force, 80 is the distance, is 0. Again, 3 equations, 3 unknowns. You get what you want. So ND would be minus 10 Newton. So minus means that it's going to be actually compressive. And, well, VD would be, let's say, 10 square root of 3, and then MD would be 1.6 Newton meter. And these are Newton. All right? So it's not surprising that one of them is minus, because you see both of them are in the same direction, basically. So one of them should be minus to cancel the other one. That's one thing. The other thing is that we did not talk about the force at A, okay? So here I just sort of naively assume that the force at A is only horizontal, but you can obviously think about it if you think of the whole piece, right? If you think of this whole piece, you see these two forces are vertical, so obviously the force at A had to be vertical. If it had a horizontal component, then it wouldn't work. All right. Do you have any question? Okay, so this was the first exercise. The second exercise today is the following. You are given a truss structure, and you know that all the members of this truss structure, they have identical cross sections of 780 millimeters squared. But you want to make sure that each of the members the stress in each of the member is less than 140 megapascal. Okay. Now, the structure is under force P, and we don't know what is P. So P is unknown. We want to basically analyze this structure and compute P such that the stress in all the members is less than 140 megapascal. What I'm trying to say is that you need to compute the force in each of these members as a function of P. So you compute the force as a function of P. And then among those, you will see one of them comes with a higher coefficient of P, okay, or higher impact of P. Okay, so that one of them would be the most crucial member. For that member, then we decide how much P would be. Does that make sense? So if, I don't know, if here you get FBC equals 5P, and here you get FAB equals 2P, then it means if this member is fine, this would be certainly fine, okay? So basically we need to design it for this member, and we make sure that the stress in that member would be less than 140 megapascal. That's what we want to do. Okay, so basically from this point on, what you have is just a simple truss structure analysis. You just calculate these forces using method of joints. So the method of joints, if you remember, works like that. So I don't know, you take point A, or you start from one of these joints. So I start from joint A, and I don't know, here you have force FAB, FAE. You know what? For the fun of it, this time I'm going to write FAE in the opposite direction that I usually tell you should do, okay? Usually we say it should be shown such that it shows tension, so it's plus. I just want to tell you that if you did the opposite, there is nothing particularly wrong, as long as you are careful about the other side. So let's just, this single one, FAE, just for the fun of it, let's keep it opposite to our usual convention and see what happens. Okay, so you have this. Now all you have to do is to write your equilibrium equations. Again, two equations, two unknowns. Well, there are three unknowns, but you know you want these two in terms of P. So it's basically two unknowns, and you get that. There is this angle theta here, which is, by the way, the same angle here and here. And these two angles obviously are 90-degree minus theta. And then that angle, if you want to see what it is, you should look closely at this triangle. You see again 1.2 here, 0.9 here. So this is basically our 4, 3, 5 triangle, okay? So that triangle is, if I just drew it here, if this is theta, this would be 3, this would be 4, this would be 5. So that means sine theta is 3/5, cosine theta is 4/5. All right, so now that you have this, you write just equilibrium of forces in the x and y direction. In x direction, you get FAB cosine theta minus FAE equals 0. Here you get FAB sine theta minus P equals 0. All right? And then, again, you know cosine theta and sine theta, they would be 4/5 and 3/5, respectively. And from this, you can calculate FAB and FAE as a function of P. So FAB would be 1.667 P, and FAE would be 1.333 P. So among the two, AB is more crucial, okay? Is the more sensitive member. Is that clear? Okay, so we have done joint A. What we want to do is to come to joint E after that. Pay attention, we cannot jump to joint B because there will be 3 unknowns. So we need to go to joint E, and then after that we go to B. So the next joint we want to do is joint E. Let me just do it on the side. Okay, so joint E. So on joint E, now this is the part you need to be careful. Because here I drew FAE as if it was compression, now you should also be careful that here you need to write it as a reaction to that, so it should also be compression on the other side. That's the only thing that you need to be careful about. So at E, you would have, now, let's say FAE like that, and then maybe you can immediately imagine FED should be opposite to that, because these are the only horizontal members, and then you would have, I don't know, FEB, and you have this thing that is 0.75 P. Okay, so this is a simple problem or simple structure. You write again, equilibrium of forces in x direction is 0. Equilibrium of forces in y direction is 0. In x direction, if you write that, you can immediately see FAE equals FED, which from the previous one, you know it's going to be 1.333p. From the equilibrium of forces in the y direction, you can see FEB would be 0.75p. Okay, so this is, so far, then this is the least crucial or the safest member. Does that make sense? So we need to do one more step, and that would be joint B. So at joint B now, you would have this picture. Let's say FBC. FAB. FEB. And okay, I'm going to write BD also as if it is compression. And then again, remember, this angle is the same angle theta, and then maybe you can call this one alpha, remembering that alpha is nothing but 90 minus theta. So cosine alpha is sine theta. All right, now that you have this one, again, what you need to do is to write your equilibrium. So you write equilibrium of forces in x direction and equilibrium of forces in y direction. I don't write the expanded version. You know by now how to do this. This is just multiplying them by sine, cosine of those angles, adding them up, setting them to 0, and then eventually you end up with, let's say, okay, maybe 2 equations, 2 unknowns, and from that you can calculate your FBD and FBC. So FBC would be 3.667p, and FBD is 2.917p. Okay, so among all the members, you can now immediately see. So this is AB, AE, ED, EB, BC, and BD. You had 6 members. These are the forces in those, and obviously this is the maximum, or this has the highest coefficient of P, right? So this is the most crucial member, and what you need to do now is to make sure that stress in that member is smaller than the allowable stress, which was 140 megapascal. Now, stress in BC itself is FBC divided by area. Area was given to be 780 millimeters squared, which is 780 times 10 to minus 6, okay? And FBC itself, what we have here is just the usual coefficient of P. But then here you have a megapascal, so that takes care of that factor 10 minus 6 essentially. And if you just insert that thing, you would get P equals 29.779 kilonewton. All right? So that's it. So that's the maximum force P you can apply, and then all the members would be, let's say, would be safe. Because the worst one, you know, the most crucial one is safe, then the rest of them would be safe too. Any question? All right. If there is no question, then we come to the next one. Okay, this is the next exercise. you have essentially these two wooden beams that are connected at points B and C. Okay, so these are two separate beams, but then you have this connection, which maybe you can see it. It's essentially a bolt with a washer here. Okay, so what we want to do is to make sure that that bolt and washer are safe. Okay, so that bolt and washer, they have allowable stresses given in the question. So what you want to do is to make sure that's true. All right, so what we need to do for this example is to take it into two separate pieces. So let's say here is FA, here is FD. What we need to do is to look at the upper piece standalone and at the lower piece standalone. And between the two, obviously, I mean, here, there would be some sort of interaction or inner force reaction, action reaction, inner force FC. Here, there would be also an inner force B. Okay? So we don't know these. And we don't care so much about FC anyway, but from FB, then we can check our design for the bolt. That's the force that the bolt is supposed to carry. Okay? So that's the idea. What we want to do is to basically take this thing into two parts, take it apart, and then write equilibrium for each of those separately. So let me just, maybe I draw it like this. For the upper part, let's assume this is FB, and this is FC. For the lower part, I use a different color. So FC for the lower part would be then the opposite of what it applies to the upper part. So that would be then downwards. And the same with FB. So this would be now upwards. Does that make sense? So now you have this picture, which is very simple to analyze, and then you have this picture that's very simple to analyze. And if you write equilibrium of moment with respect to A here is 0 for the lower member, and equilibrium of moments with respect to D is 0 for the upper member, you get two equations in terms of FC and FB, and you can calculate them. So that's essentially what we want to do now. We write it for the upper member first. So if I write equilibrium of moments with respect to D is 0. And then again, assuming that counterclockwise is positive, what do we have? We have 1.5 times 2 that causes a counterclockwise, so it comes with a plus. Then you have 3 times 1.5, also counterclockwise with a plus. Then you have FB times 4.5, also counterclockwise. And then eventually you have FC times 6, that is clockwise, so it comes with a minus. So you get minus 6 FC plus 4.5 FB plus 1.5 times 3 plus 2 times 1.5 is 0. Right? That's the equilibrium for the upper part. For the lower part, I am using, again, a different color so that it shows that. So that's equilibrium of moment with respect to A is 0, again, doing the same thing. Now, you would have this force 3 at distance 2. It will cause a clockwise moment, so a minus. This would also cause a clockwise moment, so FC times 4, also minus. But FB would be multiplied by 5.5, and that would cause a counterclockwise moment, so it comes with a plus. So you would then have minus 4 FC plus 5.5 FB minus 3 times 2 is 0. Okay? So now you have two equations, two unknowns. From them, you can calculate FB and FC, and if everything else is correct, then FB would be 4.4 kilonewton, and FC would be 4.55 kilonewton. Again, FC is not really that important here, but what we want to do now is to use that FB to analyze our little bolt and washer system. So now you can imagine the bolt itself would be basically under that much force. So that will be the inner force of B. So what we want to do now is to make sure that the normal stress within the bolt is less than 150 megapascal, which is given in the example as our allowable stress or tensile stress. And that must be our FB divided by the area of the bolt. The area of the bolt is just pi over 4 diameter squared. Now we know what is FB. And from this, you can compute the diameter of the bolt. That's 6.11 millimeters, at least, okay? Or maybe it's better to write it as larger equal. That's sigma B. So now the next thing you want to do, so this was, let's say, the bolt itself. Now you want to also analyze what happened to the washer. Now, washer is like a hollow cylinder, right? So the area of that would be pi over 4 times, let's say, outer diameter, which is what we want to compute. This is the washer diameter minus the inner diameter of the washer. And now the inner diameter of a washer is basically the diameter of the bolt, right? So that, and then the force that is applied to it is the same as FB, and the stress for that should be 10 to the power 6. Okay, so this is, let's say, sigma for the washer. It must be less than that. So that tells you the W must be larger than 15.4 millimeters, I think. Is there any question? All right. So we have one more exercise. Here. Do you have a question? All right. So we have the last exercise for today. We have the structure given here in the picture. We have 3 discs, A, B, and C, and they are supposed to support the load of 140 kilonewton. You are asked to compute the smallest diameter D, D1, here on top of the disc, the largest diameter D2 of the opening, and the largest diameter D3 of the hole at the bottom of the disc. The allowable bearing stresses for the material is 350 megapascal, and shear stress is 125 megapascal. All right, so we start from the bottom of this picture, let's say disc C. So we need to make sure that it is resisting against, let's say, shear failure as well as bearing failure. So for the shear failure, you want to make sure that the force that is applied to it on these walls, it's going to cause shear stress, right? So you want to make sure that shear stress is less than, let's say, 125 megapascal. But also you want to make sure that, let's say, the normal stress inside, in that area, let's say in this direction, or the bearing stress is less than 350 megapascal. Okay? So you want to basically analyze this here. Now for shear stress, tau is V divided by A. Now, you should think of that, as a hollow cylinder also, like this. And you can imagine this has a thickness Okay, so this is kind of the picture that we have here. Now, what we are interested in are the shear stresses on these two sides. Okay, I didn't draw the remaining part. That's not interesting, but only for these two sides. So what I'm trying to say is that what I call area is that, that area that you have surrounding that, which is pi times diameter times thickness. So that would be pi times d2 times thickness, and thickness is 10 millimeters, so 0.01 essentially. V is the total force, that is 140 kilonewton, as is given. And then from this, immediately you can, assuming that tau is less than 125 megapascal, as we just discussed, you want then D2 to be larger than 35.7 millimeters. So that's the shear criteria. So if that D2 is larger than 35.7, we know that we are safe. But then there is this thing, so it is hollow inside. And now you need to make sure that that total force, which is carried by these pieces, again, it's a 2D picture, but that means it is carried inside, this area. You want to make sure that also the normal stress is not causing any failure there. So what you want to do is now to make sure that that bearing stress, which is P divided by area, is also less than the allowable bearing stress, that is 350 megapascal. Now that force P is 140 kilonewton. And that area is, as I mentioned, it's like a hollow cylinder, so it's pi over 4. Now D2 squared minus D3 squared. Okay, so from this, then you can compute D3 to be 27.7 millimeters. Okay, or less than that, by the way. Okay, so if it is more, this is different from this one. So making D2 large, it makes it safe. But making D3 large, it makes this hole larger, right? So basically it has the opposite effect. So this should be that or smaller. But okay, again. Now that's that. Okay, so this was the disk at the bottom. So what we want to do next is to just make sure that this one is also safe. Now, this one, it also has to carry this bearing stress. So basically, if you push it, in this area, you need to make sure that your stress is less than 350 megapascal, okay? But after we do that, we will learn that this diameter is less than this diameter, which basically tells you there is also a little hollow cylinder. So we need to also check for its shear failure too. Okay, so what you want to do is now coming to disk B. Again, we start with bearing failure as opposed to the previous case, and that would be P divided by A. Again, this should be less than 350 megapascal. But this one is easy. P is 140, and A is just, let's say, that pi over 4 d1 to the power 2. Okay, so this is d1, because this is the, again, this is the area that that force will be working on. And from that, you can immediately get d1 to be, let's say, 22.6 millimeters. Or again, larger than that. Okay, but now, if you compare these two, you see D1 is smaller than D3, so that means it will also cause basically a shear on the side of it. So you need to make sure that also your shear criteria is fine. So we just check it basically. So because D3 is larger than D1, disk B must resist shear or something. So what you need to do now is to make sure that if you use the same diameter as before, or let's say if you use this, the shear stress that you get is smaller than, let's say, 125 megapascal that is allowed. Okay, so you just do the same analysis. Now you would say tau is V over A, and we want it to be less than 125. If you do it, you get 140 kilonewton divided by area, that's pi d1 times 0.2. Now, pay attention here. When we discussed about this disk, the thickness was 0.01. When you talk about this, now the disk is 0.02. That's why it carries. It has a smaller diameter, but it has a larger thickness. So eventually, it gives you 98.6 megapascal. If you used this D1, okay? The one that we calculated up there. So for D1, 22.6 millimeters, you get a stress that is smaller than 125 megapascal, so that means it's safe too. All right? Does that make sense? Do you have any question? All right, so if there is no question, then we finish today's